These are the practice problems for lesson 6. Again, lesson 6 is titled Similarity. So in these practice problems, the first one says, what's a sequence of rigid transformations and dilations, either a translation, a reflection, rotation, and dilation, that takes the smaller figure to and maps exactly to the larger figure to show or to prove that the smaller figure ABC is similar to the larger figure CEF. So one is to translate, so you can move this up, you can move it over 1 unit and up 2 units, and you do that for each point. So you can translate it up here and then dilate with a scale factor of 2. So it's 2 units. If this is the center of dilation, it's 2 units out. This is 1 unit, and this is 2 times that 1 unit, or 2 units. This is going to be 1 unit, 2 times this 1 unit, 2 units. And also you can count up this way. This is 1, 2, and then another 1, 2 for a total of 4. So this is a scale factor of 2. So ABC and CEF are in fact similar figures. That is the definition. If I can map it exactly, then it's similar. So in this case, take CDB to C prime, D prime, B double prime. Those are all double primes. Well, it looks like certainly you're going to have to do a rotation of some sort, and then probably a dilation, probably from the center of dilation at A, to take this out this way once you get it there. So how many degrees do you have to rotate it? So I'm going to zoom in. This is one of those circular grids, and each one of these angles is 15 degrees. And there's 4 of them. So how do I know they're 15 degrees? Because if you look at 90 degrees, which is this one to this one, then you just count, you're going to get 4 and another 2, you should get 6. 1, 2, 3, 4, 5, 6. Because 6 times 15 is in fact 90. All right, so each one of these is 15 degrees. There are 4 of them. 4 times 15 makes this a 60-degree rotation. So here's the 15 degrees right here. So this is going to be a 60-degree rotation. It's going to take these 2 points and slide them over here. And this point is going to move as well. It's a rigid transformation, so the angles don't change. They have to remain fixed. The length of the sides do not change. They have to remain fixed. The only thing that's going to happen is going to rotate around here. And the center of rotation, by the way, is point A. So you're going to grab, it's like grabbing this figure and rotating it around 60 degrees with the center of rotation at A. So there it goes. And now, can you dilate this figure to match figure C prime, B prime, D, B double prime, C double prime, and D double prime? And in fact, you can. Each of these lengths are twice as far. So if you go from the center of dilation out to each vertex, for the smaller triangle, that's 1 unit. And if you double that, this is 2 units. So it's a scale factor of 2. So from the center of dilation to the smaller triangle, that's 1 unit. Double that, that's 2 units. So this is 5 units actually from A to this point. So it's another 5 units from this point to B double prime. Same here. This is 2 units, 1, 2. And so 2 times 2 is 4 units. This is 2, 3, 4. So each of those lengths is doubled. So it is a scale factor of 2 with the center of dilation at A. It maps exactly. So once again, that's the definition of those figures being similar. You can take them through a series of transformations and dilations and map it exactly. It sits right on top, one on top of the other. And there it is. A, center of dilation, scale factor 2. This is problem number 2. And the directions for this problem simply say that for you to measure the angles of both of these figures and the lengths of both of these figures. They tell you that the figures are similar figures. And so what do you notice when you do that? Well, since they are similar figures, one of the things that you're going to notice is that the angles are congruent. They're exactly the same. So as you go from A, B, C, D to E, F, G, H, each of these angles are exactly the same. So let me show you that first. So what I did is I copied each of the angles from A, B, C, D, and I moved them over into their corresponding positions for E, F, G, and H. Now they're going to be reflected. So if you look back at this for just a moment, you can see that you're going to use a reflection during this activity. And so that's why these angles are positioned as they are, because they eventually are going to be reflected over a line of reflection. So let me make sure you're looking at the same thing. So A goes to A right here. B, which is right here, goes across all the way over to here. Because it gets reflected, it lands on the other side of the figure. So notice this has a vertical side to it, and that's the same vertical side here. So you can keep it straight that way. D does not have a vertical side to it, and it goes right here. So this is angle D right here. And angle C is pretty easy. That is right here. All right, so now each of these are going to be reflected over their line of reflection between the two angles. So for A, that's right here. So that gets reflected, and this angle matches exactly. For B, the line of reflection is the side right here, and this angle matches exactly as it gets reflected over. C, same thing. Its line of reflection is right here, so it gets reflected and it matches exactly. And D is a little bit harder to look at because part of D is on one side of the line of reflection and the other part of D is on the other side of the line of reflection. So this part right here, from here down to right here, is going to be reflected to the right, and this little triangle right here is going to be reflected to the left. So consequently, this triangle in the original is going to get covered up. So reflected over, and so this whole portion gets covered up from the original one because it gets reflected over. Part of it goes in one direction, the other part goes in the other direction, so it covers, this part covers the corresponding part, covers it up. So the angles are congruent. So that's one part of showing the figures are similar. The second part is there a factor, a scale factor from a dilation that takes this figure ABCD and exactly maps to this figure E, F, G, and H. And so there's a reflection. So the line of reflection is right here. To reflect this figure over the line of reflection and get the same figure reflected over that line. Then you can translate it down to here. And now I want to find the center of dilation. So we're going to do this quite a bit. A way to find the center of dilation is connect the corresponding vertices. So connect this vertex with this vertex and keep drawing that line through, extend it through. And if you do that for each of the vertices, so connect this vertex to the vertex, extend this arrow or this ray through, you're going to see that they intersect at the center of dilation, which is right here. Do that with the last one. Connect this vertex with this vertex, and it's actually at the same time you're connecting this vertex with this vertex, and draw a ray straight through, and it will again intersect at the center of dilation. So that center of dilation is right there. So now you just have to figure out the scale factor. So how much, what's the multiple, what's the scale factor for taking the smaller figure to the larger figure? You can see that it's 2 times, because the length from the center of dilation to this length, that's going to be 1 unit. And if you double that, that's going to get you to its corresponding point in a larger image. So I double it, it goes to here. I do that again. Now this one gets covered up a little bit, so the unit length is from the center of dilation to right here. That gets doubled, and it ends up right here. This unit length is from the center of dilation to right here. It gets doubled. It ends up at E. And this center of dilation is from right here. This length is from this center of dilation to this vertex right here, and then it gets doubled to G. So the scale factor is equal to 2. And so in fact, you can take this figure, reflect it over this line of reflection, translate it down to here. Now I actually translated it to a different spot. Use a scale factor of 2. It doesn't matter. It's the same thing. Use a scale factor of 2. It completely maps, exactly maps to EFGH. So in fact, ABCD is a similar figure to EFG and H. That is the definition. Series of rigid transformations, dilations, and map one figure exactly to the other figure. That means that they are similar. This is the last problem, problem number 3. What you're supposed to do in this case is show that the smaller triangle, A prime, B, C prime, and the larger triangle, A, B, C, are similar figures by taking the larger triangle, A, B, C, and scaling it down so that it exactly maps to A prime, B, and C prime. And you're supposed to identify the center of dilation and the scale factor. Well, if you take this triangle, make a copy of it, the question is how many times does it cover, how many times does it take the small triangle to cover this length to get to A? And it takes 4 of those. This is 1, 2, 3, 4. So that means that this length from A to B is 4 times as long as the length from A prime to B. So the scale factor to make this smaller is going to be the reciprocal of that. It's going to be 1/4. So the scale factor is 1/4. So you're going to take 1/4 of this distance, which is going to be A prime B, and scale this larger triangle down to the smaller triangle. And the center of dilation to do that is going to be at point B. So the scale factor is 1/4, and you scale this triangle, larger triangle, down to A prime, B, C prime, with the center of dilation at point B. It is the same thing with the next figure. Prove that these two triangles are similar by scaling the larger triangle, A, B, C, down to the smaller triangle, A, B prime, C prime, so it exactly maps. That's the definition of similar figures. You can go through transformations, dilations, and get them to exactly cover each other or to map to each other. And so how many times does the smaller triangle fit along this length, its corresponding length? 3 times. 1, 2, 3. That means the scale factor is going to be the reciprocal of that. It's going to be 1/3 because you're going to shorten or reduce this length by that fraction, 1/3. So the scale factor is 1/3. And so this length from A to B prime is 1/3 the length of A to B. So this is going to get reduced in length to A, B prime, using a scale factor of 1/3, and from C to C prime, using a scale factor of 1/3. And the center of dilation is at point A, and so that proves, once again, that triangle ABC and triangle A, B prime, C prime are similar figures.